We need a balance before we start, so let's do that. 2 nitrogens on both sides. Check. Hydrogens, can we just put a 2 here to balance out the hydrogens, and that balances out the oxygens as well. How many liters of nitrogen gas, how much of this stuff can we make when we're given that stuff? With that stuff, oh no. Now we gotta do stoic twice. Okay, let's do it. We'll just do part A first. One step at a time. We're gonna figure out if we have 1 kilograms of that rocket fuel, how much nitrogen gas can we make? Now, why would anybody care? Because 70% of our atmosphere is nitrogen. Well, anyway, it's just a stoic problem from our textbook, so let's do it. I'm going to just write 1 kilogram as 1,000 grams to save a little space. But if you need a conversion factor to do that, go ahead and do it. But I can sense that this is going to be a tight fit. So I'm just going to do some conversions right there. All right, anyway, convert to moles. 2 sig figs. All right. That means we just have to get 3 digits, or we should. What is that? N2H4. All right. N2. 14.0 times 2. 28. H4. Wait, what am I doing? H4 means 4 H's. Each one is 1.01, which is around the 3 digits here. That's times 4 is 4.04. Add that up, that's 32.04 grams per mole. I ran out of space for the units. 32.04. So 32.04 grams of this N2H4 is the mass of 1 mole of N2H4. That's called the molar mass. We use it to convert between moles and mass. All right. Next step is to turn that into the desired substance. Right now, all our information is in terms of this N2H2, and at some point we need to turn that into N2. We're going to do that using the mole ratio right now. It's a 1-to-1 ratio, by the way. All right, so it's 1 mole of N2H2 for every 1 mole of I should have said it the other way. For every 1 mole of N2H2 used, we're going to get 1 mole of N2. All right, final step. Now we have our information in terms of nitrogen. We just need to, wait, what's that asking us? How many liters? All right, so that's good. We don't need the periodic table for that. All right, this is all assuming STP into liters. 22.4 liters of any gas at STP. Somehow it's STP inside a rocket engine. Or maybe they're just burning this outside. Okay. Did it say it's in a rocket? No. So maybe I'm just blowing it out of proportion. 1,000 divided by 32.04 times 22.4. 699. 2 sig figs. 7.0 times 10 to the 2 liters. All right, we don't know if that's the answer, but we'll just rewrite it with 2 sig figs in scientific notation, because otherwise it would just be 700 and nobody would know if it had 1 or 2 or 3 sig figs. So that's when we use scientific notation, when it's not so obvious. All right, I'm going to do the kilograms of O2. So again, I barely fit that in there, so I'm going to just do the conversion right here. 1.2 kilograms is 1,200 grams. I'm trying to write that small, and that's O2. Okay, convert that to moles. Again, if you could have done, let me show you what I mean. You could have done 1.2 kilograms of O2 and then use the conversion factor. 1 kilograms of O2 is equal to 1,000 grams of O2, and then you would get the same thing. 1.2 times 1,000 is 1,200. So, but I need that space, so it's just gonna 1,200 grams of oxygen. Convert that to moles. The molar mass of one oxygen is 16, but so two of them is going to be 32. 32. Get 3 digits here. 32.0 grams of O2 in 1 mole of O2. All right, cancel. Step 2, convert to, we have now moles. Now we can turn that into the substance we're looking for, which is N2. It's a 1-to-1 ratio again. Okay, it's going to look just like the one above. Almost. All right, so 1 mole of O2 is going to produce 1 mole of N2. All right, N2 and O2. Right, N2 and O2. All right, so the last step, change that into volume. It's going to be the same thing we just did. 1 mole of N2 takes up 22.4 liters of space at STP. Okay. Whoa, what a coincidence. It's like the molar mass of the rocket fuel is almost the same, or the same, you could say, as the molar mass of oxygen. So you already know the answer here is the limiting reagent is going to be the rocket fuel. You already know. Limiting reagent, right? And if I wasn't clear, it's because all of this is the same as all of that. But you're starting with less. That's how I know. All right, anyway, we're almost done. Let's just do the calculations and we'll see. 1200 divided by 32 times 22.4. 840. 840. And again, that's not very, you don't know that if that's 2 or 3 sig figs, so I'm going to write that in scientific notation. 8.4 times 10 to the 2 liters. All right, so we have our answer. Oh, should have done that all in red. 8.4 times 10 to the 2 liters. So we got our limiting reagent. This that's the rocket fuel, and this oxygen is going to be the stuff left over, excess reagent. And in fact, we can answer the last part. It's going to be left over by 200 grams. All right, and that's because all of this is exactly the same. All right, but be very careful. It's not because I just took 200 minus that. That's not how it works for sure. This is just a very coincidence that the molar mass of it happened to be the same. So this is going to confuse some students. All right, we're going to answer B properly, right? Just to show you this stuff, right? But it is going to be 200 because everything else works the same. But here's how you would normally do it, because that's very, I wouldn't expect that to ever happen again, or very rarely. All right, so how many grams of the excess? Well, here's the excess. How much of that do we have left over? So we just need to use the moles, which we didn't save. All right, so here's what you do. You start with the moles of the limiting reagent. That's the rocket fuel. All right, so let me just copy and paste. Oh, come on. This right here. That's what we're going to start with. All right. All right. We just need to know how many moles we have of the limiting reagent. So 1,000 divided by 32.04. All right, so that's 31.2 moles of rocket fuel, N2H4, hydrazine. Now, let's find out how many moles of the excess reagent we have. Just copy and paste. We've done this before. All right. Oh, what's that? All right, and again, it's going to be the same, but normally it's not. Oh wait, it's not going to be the same because numbers are different. All right, 1200 divided by 32. 37.5 moles of oxygen is what we have. Right? So we already know the rocket fuel is the limiting reagent. This one we know. So we want to know how much of the extra stuff is going to get used up by that limiting reagent. Rewind the video, play that over again if you need. All right? We want to know how much of this stuff we have excess of, more than enough. How much of that is going to get used by the stuff that's we have less of. And then whatever's left over is going to be your answer. All right, so let's do it. Start with the limiting reagent. The moles of the limiting reagent is 31.2 moles of N2H2, right? And then the mole ratio is 1 to 1, right? So here it is, 1 to 1, O2 and the rocket fuel. So 1 mole of N2H2 for every 1 mole of oxygen consumed, 1 mole of the other stuff is consumed. All right, so this is what I was saying earlier, is like 1 over 1 is just itself, so you're going to end up getting the same number, 31.2 moles. Oh, running out of room, smaller. Too small. 31.2 moles of oxygen is what's actually going to get used by 31.2 moles of rocket fuel. That makes sense because their mole ratios are 1 to 1. But we started with much more than that, so we just got to subtract the 2. Right? So 37.5 moles is how many moles we started with, but only 31.2 moles actually got burned up, got actually used in the reaction. So that's going to leave us with 6.3 moles of O2 remaining. Remaining. But I'm sure it didn't ask for moles, did it? Probably asked for like mass or, yep, asked for how many grams. So we need to convert that to grams. All right, let's do it. Moles of O2, grams of O2 is 32.0, 16 times 2 is 32, is the molar mass. All right, now this is going to turn out to 200. Whoa, Mr. Lee, how'd you know that? 201.6. All right, anyway, we need 2 sig figs, so it's going to be 200 grams of O2. All right, or 2.0 grams. So what are we doing? 2.0 times 10 to the 2 grams of O2. Or you could write 0.20 kilograms of O2. They all mean the same thing. I'm going to circle this. All right. You may be like, whoa, how'd you do that so fast? Well, that's what I was saying at the beginning is just this all is exactly the same. So this is just 200 times more than that. But again, that's rarely going to happen. This is just a bad problem for many reasons. But anyway, I did do it all step by step as you would do it for any problem. So I hope that helped.